Most of you. How many people are business people then? Some of you. Okay, great. So today we're going to talk about AI as a service. I'm hoping that the end of the end of this talk, you're going to come away with wanting to go create your own little deep learning system really quickly, right? And how do you do that is pretty much most of my talk. So we're talking about autonomous machine learning. Like Bill said, I had a stint at AWS where I did a couple of services. Before that, at a company called Post Intelligence. Before that, Google. So I've done a lot of machine learning systems. I've pushed a lot of machine learning systems into production, and a lot of these big companies, especially the trillion-dollar companies, are obsessed with AI. I think we all know that, right? Why? Because it can be transformational. In fact, the talk just before us from Compass, it was very obvious that Compass became a really big company or became a very successful company because obviously they took a very AI-first approach. So something which everyone ought to do if they aren't already doing. Now, everybody knows about FANG, correct? A lot of you people probably dabble in stocks too. So the thesis we have is one of the reasons the top 5 companies in the world are these companies, or 4 of those 5 companies are on this slide. It's primarily because they've taken not just an AI-first approach, and this is very key, they've also taken a deep learning-first approach. And deep learning is a little different from your classical machine learning. How many of you are very aware of deep learning? Quite a few, right? How many of you are fans of classical machine learning? Okay, some of you. So a lot of these companies, obviously, as you can imagine, years ago, started with classical ML and kind of have moved almost completely to deep learning. And what deep learning has enabled them to do is to scale to millions and then billions of either products which they can actually deliver to their houses, to the news feed which you see every day on Facebook, and most importantly, actually, I'd like to call out YouTube here. One of the things that people miss is that one of the biggest successes of Google over the last decade has been YouTube. And the reason for YouTube's success is literally one algorithm. It's called YouTube Next. It's a recommendation algorithm which figures out what video to show you next based on who you are. And they've worked on this and worked on this. And right now, it's probably the best recommendation algorithm there is in the world. But it's basically increased engagement on YouTube, at least by a magnitude of order, and gotten them to the trillion-dollar market cap. So here's why deep learning matters. For all the classical machine learning enthusiasts, they'll probably tell me, hey, look, classical machine learning has its own place. Deep learning has its own place. While that is true, all the research is where deep learning is today, right? If you go to a NeurIPS or an ICLR or an ICML, all you're going to see is people coming up with supervised learning or unsupervised learning papers. The big advantage deep learning brings to the table is you don't have to know which features matter. Now, what does that mean? So just again, in the talk before, we talked a little bit about real estate, right? And we talked about the various different features that would matter there. And if you're a classical machine learning specialist, what you would do is you would really go deep into that domain. You would be like, okay, number of bedrooms matter, number of bathrooms matter, maybe in search, this particular thing matters. So you'd have to have a lot of knowledge. With deep learning, what you can do is pretty much take all the data you've got, train a neural net on it, and hopefully the neural net will actually discern patterns from it. And in almost all cases, especially when you have enough data, it beats classical machine learning. So it's not even like you need a ton of data points. We've done a lot of research on this. And if you have more than 10,000 data points, you can actually run a deep learning model. With 50,000, you're most likely going to be more accurate, or you're going to have more accuracy than a classical ML model. Most enterprises and most companies you probably work for have enough data. And of course, the biggest reason why anybody should care about AI is you can go beyond traditional analytics techniques, and your ROI goes up from almost from 30 to 128% if you actually implement after you've implemented a machine learning model. This comes out of a McKinsey survey, which was conducted recently of more than 1,100 companies. So really, why all this fuss about deep learning? It was actually invented in 1943, so it's a really, really kind of old technology, nothing new to see here. But it would take tons and tons of time in terms of compute to actually train a neural net. The other issue was you needed a lot of example data. So what happened was, over time, obviously Moore's law got kind of got to see the light of day, and compute got exponentially faster. Obviously, you got tons and tons of data, especially because of the internet. And really, 2012 was what I'm going to call kind of the revival of AI. So the winter of AI was gone. AI came into fashion all over again, primarily because there was a huge victory for a deep learning model called AlexNet. AlexNet was invented by these three people. Geoffrey Hinton, of course, is one of the fathers of deep learning. The other two people are really famous as well. It was basically AlexNet won the ImageNet challenge. And the ImageNet challenge was simply nothing more than classifying, actually that's right here, a little bit go back there. It was basically to classify images in a large library which had more than 14 million images, right? Again, to the point that someone made about computer vision, this was a computer vision model which basically identified different classes based on, from a large data set just by training a neural net. And this particular model did much, much better than pretty much anything else that was out there. And the history of deep learning basically goes to all the way starting from a simple CNN, in 2011 over the last few years, to basically having Jeff Dean and Andrew Ng actually have an experiment where they actually managed to find a cat in a bunch of YouTube videos where there was, where the machine did not even know what a cat was. So basically, it started to see in so many ways. And a lot of people talk about vision, talk about language, and so on. Everybody's fascinated. But the truth of the matter is, in enterprises today, AI is pretty rudimentary still. And that's actually a really big opportunity for all of you out here, right? We can actually go create really interesting AI and deep learning systems. Today, if you look at a typical enterprise, let's take someone like, say, Nordstrom or Nike or what have you. You're going to see that most of the systems that they implement are typically based on statistics. The other thing is they're rule-based systems. How often have you implemented a rule and the rule kind of sort of works? Classic example is in fraud. If you said, hey, if somebody logs in 5 times and they're still trying to log in again with the wrong password, you lock out your password. That's a rule-based system. The other big problem is a lot of people struggle with this. The data is trapped in some place or the other, right? So overall, we think we're really early. So it's still early days for enterprises. While the trillion-dollar companies have really kind of adopted deep learning, most enterprises still are have many roadblocks. And most of the gist of the talk is, what are these roadblocks and how do we overcome them? How do we make it so that AI and deep learning is really democratized and really available to every single enterprise there is, right? And these are the biggest roadblocks as we see to AI adoption. The first one, picking the right problem to solve. While computer vision might be really sexy, it's probably not an important problem for most enterprises. How many people deal with images? Not that often. And so I wouldn't go off and pick vision just because you hear about vision a lot, right? So you need to know which problem to pick so that you get the biggest ROI. Second, shortage of talent. One of the biggest problems we have is not enough people who know how to create deep learning systems. And this is not just science, it's engineering, it's data engineering, it's DevOps. It's a lot of different people coming together. And then there's actually not many tools that work. So how do you pick the right problem? The first thing to consider is the data that you have. There's different types of data, language, vision, tabular data. I like classifying them in these 3 different ways because there are different approaches that can be applied to various different types of data. I would pick the data that you have as opposed to the sexiest problem there is. The second thing to do is your data labeled? And by this we mean, and this is something which you probably have heard a million times if you've gone to some of these talks, today deep learning and any kind of learning really works really well if you have very good labeled data, and that's supervised learning with high accuracy. For people who don't know what labeled data is, it's very simple. If you have a bunch of images, and if you don't know what's in those images, that's unlabeled data. If you know exactly what's in those images, whether they're cats or people or whatever, that's labeled data, right? So if you have labeled data, things work really well. There are new techniques for unlabeled and other types of data as well, but having labeled data helps. Having said that, the new revolution over the next decade or so, if you're one of those people who's writing scientific papers, I would largely encourage you to think about unsupervised learning, because that's where all the action is of late, which is basically what happens if you don't have too much labeled data. The other thing which gets missed in a lot of these kind of like conversations is tabular data. To be honest, most of us have tabular data, right? Over images, over anything else, what do we have? We have data in databases. We have data about users. We have data about like our products that we sell. We have data about potentially kind of like access logs, which user used what, when. So one thing, if you want to look at tabular data, I would say that most enterprise use cases are a little bit more around like things like scoring, recommendations, anomaly detection, search, and so on. So something to consider when you're picking the right problem. The second issue is shortage of talent. Okay, why does talent matter? A lot of people think that having a notebook which has a model is all you need to get AI into production. That's like 1% of what you have done, right? You have to take that notebook, you have to retrain your model, you have to set up data pipelines, you have to make sure the model doesn't die over time. You have to also make sure that the predictions are good over time. And then you have to make sure that everything is working and there's no errors in your data on an ongoing basis. This is really, really difficult to do. I'll give you an example. Somebody like Google has around 500 people working on the YouTube recommender system. So you need anywhere between 500 to 1,000 people on a large-scale system. And I would challenge you if you tell me that you have a deep learning system in production and you did it with like 5 people, however small, right? It usually takes between 10 to 15. So it's very expensive. And it's not just getting the data scientist. And usually the data scientists need a lot of like kind of support systems after that. And on top of all this, the state of the art changes constantly. So it's not like, hey, you got something up there, literally 2 weeks later, there'll be a new model. I don't know if any of you do language research. You will see that in language especially, Google will say they've got the best language model. Literally 2 weeks later, Microsoft comes out and says they have a bigger language model. So you're going to be stuck trying to like keep up with the state of the art. In terms of tools in AI, there's a lot of them. It's actually a very, very crowded space. But what you want is a tool that actually works. It reminds me, we're at a time, I think, kind of right before the iPhone age. I don't know how many of you are old enough to remember this. There were like thousands of WAP phones, right? You would have all these Nokia phones. You would have phones from Motorola. And everybody would have their favorite phone. And no phone did well. And then suddenly one fine day, Steve Jobs showed up. And there you had it. You had that best tool, the best phone there was, and everybody decided that that was the phone that they would buy. In the AI world today, we're kind of in the pre-iPhone phase, and there's no really big winning tool yet. So there you have it. I mean, there is an opportunity because there's a big need, because all of us really do want to like go off and create those deep learning systems. We want to do it as cheaply as possible, and we want to do it as accurately as possible. So what we're proposing, and again, this is not to say that our startup has the answer. This is actually to say that this is a big problem. So the reason why I spent all these slides was not to go off and pitch like, hey, come use Reality Engines or what have you. It was basically to say this is a huge problem, and it is a huge opportunity, and we need to solve that problem. And the idea is AI as a service. How many of you use cloud today? Any kind of cloud, Azure, GCP? Quite a few. And as you know, there's a lot of movement towards the cloud. Why is there that movement, right? Why don't we just like go off and like buy some machines, put it in our like whatever backyard and like turn it on? The main reason is that it's not, after some time you can't manage it. After some time you can't scale it. After some time you can't keep it up to date. And anybody who's kind of, and of course the cloud has its issues too that we're figuring out. But the thesis here is that AI also will move towards more of a service-oriented space where you can actually use AI as a service. So the idea there is to say, even if you are an engineer who doesn't know too much about machine learning, you should be able to build state-of-the-art, cutting-edge machine learning systems. And you should be able to deploy them, test them, experiment with them, and to be honest, customize them. Like, I completely understand that you need to customize stuff. And so this is the approach we propose, which is what we're calling a layer cake approach to APIs. So if any of you are ever designing APIs, I strongly recommend taking a look at this approach at least. So especially if you have internal clients that you are like servicing, or if you have external people who will use your API, always come up with a top layer of the API which is really simple to use. 4 or 5 calls, and voila, you have something. Because people, developers especially, love the idea of like building something, right? And getting it done easily. So you want the first kind of instant gratification to be that first layer, where you don't need to know any machine learning. But then let's say you've done your first thing. It's pretty simple. Like, it's like Legos. When you first build your first Lego thing, it's simple. You know, a 2-year-old can probably do it, maybe a 3-year-old. But a 3-year-old probably do it. But then you have like really complex, Lego bricks, which you can put together to get, create some very fascinating systems. Similarly, you want to design your API, and this is why we think for AI as a service, an API like this makes a lot of sense. The middle layers will allow a lot of customization, a lot of flexibility and tweaking. And finally, the bottom layer, where if you're an expert, you can pretty much plug and play your algorithm. So let's say you're really into algorithms, which I think is the most fun part of this, this whole equation. Then you don't want to worry about the rest of it. And there is a lot of the rest of it, right? If you look at it, there are multiple different modules which go into an AI system. This is, if you go to any VC firm today, they'll put this slide up. I'm not kidding. You know why? Because they're either funding companies which are like focusing on one of these modules, or they're funding companies which are focusing on all of these modules, right? And this is really important because these are all of the different pieces of the puzzle you need to create a machine learning system. The two light blue boxes are kind of like nice to haves. Think of them as the icing on the cake. The dark blue ones, absolute must have. You cannot create a system without those modules there. Each of those modules are pretty complex to make work in the sense that you have to keep them running on an ongoing basis, right? So the ideal scenario is what you want to enable, if you're a business person who wants to enable the data scientist, or if you're a data scientist or an ML engineer, you want to have someone take care of all of this plumbing. If you work for a large company, let's say, I don't know, let's say Samsung, right? Or some large company like that, you want to be able to build all of these pieces yourself and offer a service like this. To be honest, there is some version of this working inside of a Google or a Facebook, not completely feature perfect, but there is some version, so that there are thousands or tens of thousands of data scientists and machine learning engineers can actually really plug and play AI into such systems. So you need all of the plumbing. Now, once you've got all that plumbing done, I didn't go through the parts of the system because I know a lot of people said here that they were ML engineers, but you can come talk to me later if you really want to go deep into like what are the parts of an ML system. But at its core, you need data ingestion, data pipelines, model training, and hosting. But then here's the problem. That doesn't just solve it. There are also other hard problems that you have to face. The big one is training with less data. How often do you deal with data problems? Anyone here dealing with data problems, building ML systems? So quite a few, right? So what do you do if you have less data? There are a lot of interesting methods you can use, especially with deep learning if you have less data. With classical machine learning, you can't do much. Second is AI-assisted ML. This is more if you want to build a platform of sorts, which will basically create an expert system, which will in turn create a model. And the third problem, which is a huge big deal and probably the hottest thing in VC AI as a service in the VC market, is explainability, which is how do you explain deep learning predictions. Now we'll go a little bit into each of these three things. This gets a little bit more technical, but not too technical, so I think most people can, will probably be able to follow along. And we want to focus on these three big problems we think are key to making AI as a service, or actually building an autonomous machine learning service. The first one is what happens if you have less data, which is a very common problem. Less data is the same as noisy data, incomplete data, all kinds of data issues, basically. There are multiple different techniques you can try. The first one is data set augmentation. It's pretty interesting, and it's very new. And the idea there, actually, to be honest, data set augmentation is actually a little old, but there are new approaches which are very interesting. But the idea there is augmenting your existing data set with other data. So that's basically what data set augmentation is. Meta-learning. Meta-learning is another very hot PhD topic. The idea there is to train models which learn to learn. So instead of having to train a model every single time, so as a classic example, computer vision is one of those. Instead of having to customize your model for real estate, or customize your model for healthcare, or customize your model for everything, what you need to do, what in the future we're going to see are models which learn to learn on very few samples of healthcare data, or very few samples of real estate data. So you don't have to go and recreate models every time. Transfer learning, you basically train one model, and then you can then use very little data to train another model which is customized for a particular case. And finally, we talk about deep neural nets combined with logic rules. So let's talk about data set augmentation. So in computer vision, a very common technique, actually I think Jan LeCun invented it some time ago, is using data set augmentation to kind of make your vision model more accurate. What that is very simple. Let's say you have 10 images of cats, right? And your accuracy is, let's say, 20% or 30%, so it's low. You can take these images of cats and rotate them, change their poses, change the lighting on them. And now suddenly you can have 40 images of cats because you just augmented the data, changed it. Now you go train a model with those extra images of cats, your accuracy goes up. So that's kind of nifty, right? Suddenly you can add more information by just rotating images, changing their poses and so on, and creating a more accurate model. But what's even more interesting is this thing called generative adversarial networks. It's a very, I would say 2014 is probably when it got invented by this guy called Ian Goodfellow. And what generative adversarial networks does is generate deepfakes. You probably know about this already. I think there's some talk about deepfakes today. But there is also very good kind of use for GANs. And GANs basically help you take a raw data set and create a synthetic data set. So that example where I gave you where you have a few images of cats, you can use a GAN to create more images of cats. Once you do that, you suddenly have a bunch more cats than you started with, and your accuracy improves. The way a GAN works, and again, we can go deeper into this if need be, but at a very high level, all you need to probably know is there is a generator neural net and there's a discriminator neural net. The generator will generate a cat sample. The discriminator basically just says, is this a real cat or a fake cat? The discriminator is actually trained to learn, distinguish between real and fake cats. The generator basically keeps on generating images with the idea that it can fool the discriminator. So think of the discriminator as a human, and I'll keep showing you pictures. You're like, no, that's not a cat, that's not a cat, that's not a cat. And suddenly you're like, yeah, that looks like a cat. So suddenly you've generated a cat. So that's pretty much how a generative adversarial network works. What basically it does is it helps you unlock the information in a data set, so you can actually take a very small data set and produce more images and improve accuracy. Classic example, this is something we actually worked on. We have a paper in NeurIPS about this, which is we took a bunch of pictures of produce, like apples and beets and whatnot, and we just used a GAN to produce more of the, more pictures of the same fruit, and by increasing the amount of samples, we increased our accuracy significantly. That's a 15% increase in accuracy, and in the deep learning world, 15% increases are very, very significant. Another approach, meta-learning. Meta-learning is the idea of teaching a model to learn so that you don't have to teach it every single time. The problem of customization becomes much easier if you have a meta-learning model. And what the meta-learning model does is, the way it works internally is models will be trained over a multitude of learning tasks. So what's really happening there is you train a meta-learner, which actually then trains another learning model. And even with a very little samples, or very few samples of the actual new data set, it can learn a new task based on that. The third approach is transfer learning, right? Again, I don't want to go too deep into this unless somebody in the audience or the audience generally feels like I should spend more time on each of these techniques. But it's probably good to just remember the names of these techniques. You can obviously go look them up. Transfer learning is pretty much the key behind all vision and all language models today offered in, say, Google or in GCP or in AWS or where have you, because the fundamental point behind transfer learning is very simple. You train a very large model based on all the images there are, right? So you take a corpus of all the web images, say millions of images, and so the model learns how to actually distinguish characteristics in an image. And then now say you have a healthcare client, or let's say you have a real estate client, and you want to really customize your model for their benefit. And the way you do that is you take this pre-trained model and retrain the top layers of the model with samples from that domain. So suddenly you're not having to build a whole computer vision model just for real estate or for healthcare. You're actually taking a pre-trained model and retraining it. Now this tends to be way better than actually starting things from scratch. Why? Because you don't have that many examples in your domain, right? Let's take healthcare. The number of cancer photos you're going to have are going to be no more than 1,000. You're not going to have 1 million photos of people who have breast cancer or like skin issues or what have you. And the way to create accurate models in this case is using transfer learning. And this is something which you can actually do today. Same with language. You can you can take a pre-trained model like BERT and retrain based on your data sets, and it'll actually give you a lot more accuracy. Classic example here with transfer, you will see that the performance is much higher than without transfer. Again, another reason to do deep learning over classical machine learning is things like transfer learning is even possible. The next thing, this is a place where we've done a lot of research for what it's worth. Our company has a research lab as well, which focuses on a lot of these problems. And this is something which is really kind of like, I would say, newish over the last few years. CMU is one of the leaders in this area. And the idea there is incorporating logic rules in neural networks. How often do you feel like, hey, my rule which says more than 5 accounts, 5 logins are bad is good enough? Meaning, I just need to put in a rule when people log in to detect fraud. If you don't get your password right 5 times, you're out, right? That's a rule, and that works well. And now people are very unhappy when someone tells them, hey, let's use a machine learning model to detect this. Let's throw your rule out, and let's use a machine learning model. And a lot of times, like maybe 90% of the time, the machine learning model will get it right, and then there'll be a 10% where it won't. So then you're like, look, the ML model doesn't work anywhere. So the hope is that we actually incorporate both. So you have some information which says that 5 logins or 5 failed logins is is probably a bad actor. Let's incorporate that into the neural net. So let's give that extra information and see what it does. So the idea there would be that maybe it's not 5, maybe it's 4. So your rule was rigid, right? So maybe there was a problem where even the 4th one should have been flagged, and by not flagging it, you might have had a hole in the system. But if you add that rule into the supervised deep learning model over time, the idea is it gets more accurate. So this is very applicable when you have a lot of prior knowledge. Another example where you can use rule-based systems is recommender systems. So for example, if you have women who like to buy high-heel shoes, women like to buy high-heel shoes, right? You know that. That's a rule. You want to be able to incorporate that into your ML model. So we've done a bunch of work around this. There are a bunch of papers as well. We've basically trained deep learning models which basically have some of these constraints into we took a very simple data set. This is the MNIST fashion data set, which is available publicly. And the idea there was to basically make up some constraints around what can be in a set, meaning the fashion data set was used to kind of model sets being clothing sets. Like you can't have, let's say, boots with this dress, right? And so we added a few constraints and then trained the model, and it turns out that the model, when trained that way, tends to be much better than if you don't have those constraints. The point I'm making here again is these are all approaches which you should try on your data. And if you want to use, there are many ways you can do this. You can actually go to GitHub and try to get some of those models. A, you can read those papers and replicate those models. B, C, at the risk of being self-promotional, you can come try out our service at RealityEngines.ai, which is available in beta, and you can see some of these services or some of these techniques in action. And this finally is probably the heart of AutoML. I'm sure a lot of you have heard the word AutoML or automated machine learning. Pretty much this is what it is. There is no company in the world except maybe Google, and I would say now us, who offer this as a service. The way this works is this. Basically, given your data set, we'll find the best neural net that fits your data set. So it's based on your use case and on the data set. And what we do is basically search for a range of neural net architectures and try to find the best one. And once you find the neural net, you can then tweak it to really be absolutely customized to your needs. So this is actually in a lot of cases, and we've done this with Kaggle data sets. We've done with a bunch of other different data sets. We've seen that this approach is way better than humans tweaking the data set, right? And there's actually a blog post by Google, I think, a few months ago where they did this too. And we've done this for domain-specific neural nets. And it turns out that humans can't go through millions of neural net architectures to find the best one. You actually need the machine to do it. So the neural architecture search is another, I would say a hot topic in research. What we're basically doing is, given your data set and given a use case, we basically look through, we have a search strategy, which we use based on the domain, and then we have an evaluation method, and we try to pick the best neural net that fits your data set and your use case. Eventually, explainability, probably a big problem with healthcare, also with finance. So if you're in fintech, this becomes a big issue. Mostly, people will be like, hey, if you're in fintech, you cannot use deep learning. Why? Because deep learning does not give you explanations. Good news, we have a new feature, a new invention called SHAP, or Shapley values, which helps with explanations. Now there's a lot of services offering that to you too, like very new services. We offer that as a service, so you can actually use your deep learning model and actually get explanations for them as well. In conclusion, I would say that AI as a service is a really, really big market. Pretty much everyone everywhere would want to use AI, just like how everyone everywhere wants to use the internet or wants to use technology. It's almost like software. And also, there is a cost to, I don't know if I'm running out of time, but I think I'll finish in like 2 more minutes. And with this thing that we are going to like leave behind in your heads, hopefully. Large disruptions, cause like kind of earth-shattering changes, right? Like in the internet revolution, when it happened a few years ago, 15 years ago, a lot of organizations just failed because they refused to adopt. Barnes & Noble is a classic example. Some organizations adopted and thrived. And Costco, Walmart, classic examples. And the AI revolution, like the internet revolution, will give rise to a few like mammoth companies. The internet revolution gave rise to Amazon and Google. Hopefully, the AI revolution will give rise to 2 new companies which we've not heard of. And also, tomorrow's enterprise is going to be decentralized. I think some companies have already adopted this. They will iterate and innovate rapidly, and they won't waste time reinventing the wheel. Again, another reason to have AI as a service, just like how you have cloud as a service, just like how you have any compute as a service, you don't want to keep redoing what every other company in the world is doing. And I think the person before me said it, you want to be AI first. If you're not thinking how machine learning or AI is useful to you, you're behind your competition, most likely. You also want to go beyond the obvious things, like go beyond obviously automating existing processes. Think of new ways in which AI will enable businesses. As a classic example of that is, the mobile phone showed up, and everybody was like, oh, okay, cool. We can go and like order things on the mobile phone. Yes, you can. You can go order shoes or whatever on the mobile phone. But what did Uber say? They said, hey, with the mobile phone, I can actually not just order the car, but the car can track where I am and come to me. So it's something which the mobile phone enabled, right? So you want to really think about what AI can enable, which you couldn't have done before. And I think that's when you have real innovation. Anyway, if you want to check out our brand new service, it's in beta still, so you'll have to get an invite. We actually are currently, I think we'll actually open up a few more invites later this week. But some of this stuff is covered there. You get to create your own deep learning model with the top layer, and then actually customize it as well. That's pretty much the end of my talk.
Great, thanks. Let's just take maybe a couple of questions before our lunch break.
Sorry if I ran too late. Lunch is 2 minutes away.
Yeah, the question about like the concept of the searching the architecture of the deep learning and all that. So is it just purely the search of the architecture, or can also fuse the architecture? Like, for example, you have the, Google has a deep and wide net.
Yes, you fuse. So it's not, when I said the word search, it's not just like searching through things. It's like it creates combinations and then tries to find it.
Hi, question on the augmented data set. So when you said that we have limited data set, you can augment it by positioning, change the lighting, and whatever you might have from that 10, right?
Yeah.
So the question is, wouldn't that be causing a bias to what you're trying to learn as a feature? For example, cat may have like this size, but there are cats another size.
Yes.
How do we
Of course, yeah.
make that
Augmentation is not the end-all, be-all. You're absolutely right. It does. Sometimes if you've never seen a cat which is, let's say, big or green or whatever, you don't get to see it. It does improve accuracy for, within that kind of probability distribution. And there are different ways to tweak it so that it can actually produce bigger cats too. So there are kind of like levers that you have which say go off from that distribution. But if you go off too much, you will produce non-cats. right? So that's one issue. So it's not like the end-all be-all answer. The second issue is, the second way to actually think about bias, and there are lots of biases, but there's new ways you can debias models, right? Or you can at least measure models, measure if the model is biased or not. So what I would recommend is doing augmentation, but at the same time also using a debiasing technique to see if you're biased in a particular